everyone. I have the today pleasure of hosting Stephen Wolfram. Stephen, nice to meet you, and thank you very much for taking the
Nice
time
to
to
meet
be
you
with
too.
me today. So I will go right in and then ask you, because I have a lot of questions, especially around automation and as well as computation and how today's large language models are changing, how work is done, but also how language is interpreted and what we think we understand about them. To go deeper, like from your perspective, like what are the key differences, both in some philosophically and technically, between some of the capabilities of the two systems of large language models and the, the giant computational infrastructure that you built that is Wolfram.
So, last 40 years or so, I've been trying to formalize the world in terms of computation. So kind of building a computational language for describing things in the world and computing things about the world. And that's now our Wolfram language technology stack. And kind of the idea there is to to be able to make sort of a precise formalization so that you can kind of build an arbitrarily tall tower of computation. It's kind of, that's kind of the direction that I've been going, is to formalize things so you can kind of build up a big tower of computation. What large language models and current AI is really concentrating on is doing things that are a bit more like what unaided humans tend to do, which is something broad but quite shallow. I mean, we can talk about things, we can use natural language and so on, but if you ask us to run code in our minds, we really can't do that. It's a different type of thing. Now, if you go back to, I don't know, the 1600s or something, before sort of the formalization of science through mathematics and so on, then if we'd gone straight from that to large language models, I don't know, we might, I'm not sure anybody would ever have discovered, calculus and sort of mathematical approach to science and in the end computation. But we do have that. And that allows us to do lots of kinds of things that the unaided human can't do. And I guess I've spent a large part of my life kind of living the AI dream of being able to go from sort of a thing that I imagine to a thing that I can actually work out computationally pretty efficiently. And that's, that computation piece is sort of a superpower that lets one go beyond the things which one can do with one's kind of unaided mind. And I think the LLMs are doing kind of the kinds of things that we easily do with our unaided minds. They can do it faster, they can do it on broader amounts of data and so on, but it's sort of the same general idea. It's a different idea from this idea of sort of systematic formalized computation.
Your like meta mathematics work, you've described the Ruliad, the limit of all possible computations that could happen. And if the Ruliad is a vast mathematical landscape, where do LLMs fit in that space? As compared.
Yeah, I mean, uh, I don't think LLMs have a great place there, in the sense that the Ruliad is this kind of thing that represents all of these kind of computational processes, all these things that one can do with computation. I think the LLMs are really kind of things that recognize kind of human-like patterns. Most of what's out there in the Ruliad, most of what's out there in metamathematical space, in the space of all possible mathematical derivations, most of what's out there is incredibly alien, incredibly non-human. It's really very unsuitable for LLMs. The parts that LLMs can do are to get kind of the human texture, perhaps human choices, but certainly human texture of what's done, for example, in mathematics. So it's very easy to get an LLM these days to produce something that sort of walks and talks like a math paper, even though it's actually all nonsense. But the texture of it, it looks like a math paper. It doesn't have that kind of formal structure that you need to kind of get math right, but it does have the kind of the human level gloss that makes it kind of look like mathematics. And I think that's so when it comes to the Ruliad, it's an interesting question to what extent the kinds of things that we humans pick out as being interesting in sort of the infinite space of all mathematical possibilities, the things we pick out as interesting are things that an LLM could also say, yes, I recognize that. That's kind of something that's likely to be interesting to humans. I have to say, my experiments along those lines have not been terribly successful. That is, the Ruliad and mathematical space is sufficiently alien that I don't think the LLM gets much of a kind of a handhold in the whole thing. It just sort of flails around. Occasionally it can see something that's very much like what it's used to seeing from having kind of ground up, human written papers about mathematics and so on. It'll see some little expression that's kind of reminiscent of this, and it'll kind of latch onto that. I mean, I tried an experiment recently. I was interested in a proof that I did with automated theorem proving 25 years ago, actually. It's kind of the only known example of a theorem that's been proved by automated theorem proving for the first time, that wasn't a theorem that was already at least very much believed to be true as a matter of sort of traditional mathematics. It's a theorem about what the simplest possible axiom for Boolean algebra, for logic, is. And the proof that I found with automated theorem proving is a long, complicated proof. It's got hundreds of steps. If you unroll it, it's like 83,000 steps long. It's completely human incomprehensible. I mean, I've tried to understand a bit. I'm not the best person to try to do that, but a bunch of other people have tried over the last 25 years to understand this proof. You can't get anywhere. By step 3 of what the automated theorem proving system did, you've got incomprehensible kinds of lemmas. So the question that I asked was, could an LLM somehow help me understand this proof? Could it go into this sort of path in mathematical space that had been carved out by the automated theorem prover, and could it sort of humanize that path? Could it kind of make that path something that had some kind of human narrative behind it? Well, that was a complete flop. I mean, it found some trivial things. I thought maybe it had found something interesting because it told me that, this particular lemma was a bit like some things called Mufang loops. So I go look up Mufang loops, and yeah, it's not really right. It sort of got the, if you'd kind of looked at it from a distance, with slightly fuzzy vision, was kind of looked roughly right. But when you asked for, was it precisely right? No, it wasn't. Now, I think this is, what can the LLMs capture from the 3 or 4 million papers that have come out in the history of human mathematics? They certainly can capture the overall sort of texture of those papers. Can they capture the kind of deductive sequences of those papers? There's sufficiently, doing computation is incredibly efficient, and doing things by sort of pure reasoning is very inefficient. I mean, it's like when Wolfram Alpha came out in 2009, it was kind of at a low point in the history of AI. So people just said, well, AI is never going to work. There were nevertheless a few people who were trying to sort of build common sense reasoning systems and so on. And when Wolfram Alpha came out, they pretty much said, okay, we give up. This is not, because Wolfram Alpha could just grind through and do the things that they had tried to make common sense reasoning systems do. We could just sort of blast through the answer. I mean, the way I put it to them is that what they had done was kind of the natural philosophy of the world. They had kind of tried to get to the point where you were working out what happens in the world by pure reason, so to speak. To figure out what happens in some physics problem, you would reason that this moves this, and that goes down, and this thing goes up, and so on. We were kind of cheating because we just turned that question into a math problem, just ground through kind of blasted through the math using algorithms and using computation, then got to the answer. So it's a different path. The LLMs get to do the reasoning type path. Now, what patterns of reasoning are there that may be relevant, for example, to mathematics? One thing that people were pretty surprised about when LLMs started to, after the ChatGPT moment where LLMs really started to work, one of the things that people found very surprising is that LLMs could kind of do logic. I think the reason is because LLMs kind of saw patterns of explanation, and they did the same kind of thing that Aristotle had done, which was to notice that there were certain patterns of explanation that were repeated, and those became kind of the syllogisms of logic that could then be applied as sort of templates to arguments in lots of other places. So that's sort of how the LLM kind of learned logic. Now, what are the higher level kind of logic-like flows that we can think of in mathematics? We certainly know low-level ones, which are very efficiently implemented computationally. are there kind of bigger arcs of kind of mathematical, of sort of humanized mathematics that maybe we haven't recognized so well? I mean, that's certainly what seems to have happened with language, in the sense that, why did ChatGPT work as well as it did? I think the number one reason is because it picked up certain kinds of regularities associated with language that we didn't readily know. I mean, we knew that there was grammar that said that, in English, most sentences go noun, verb, noun, but we didn't have sort of more semantic tagging rules for that. We didn't know which kind of noun goes with which kind of verb, goes with which kind of noun. And ChatGPT, the LLMs, had sort of found a pattern for those things, which they could then use in actually producing sort of meaningful text. And I think it is perfectly possible that with sort of vast amounts of kind of mathematical activity and reasoning, that maybe there are some sort of arcs of mathematical structure that we haven't recognized yet. I know, we are the number one source of kind of mathematical training data, and we've generated lots and lots of it. It's quite non-trivial you both have to be able to solve the math, and you have to be able to figure out what math is kind of what the distribution of math that's interesting to look at is. But that's something we've done, and I don't know what's going to happen. I mean, people have been using our training data. We'll see what comes out of it, and whether there's sort of a discovery of a sort of arc of mathematics in the same way that logic is sort of a discovery of the arc of reasoning for those kinds of things. I think it's the sort of interesting questions there. I mean, sort of studied quite a lot the foundations of mathematics, and I think this question that we're talking about now is really a question about human mathematics. It's not a question about mathematics as mathematics could conceivably and formally be. There is no such, there sort of all possible paths exist there. It's not something where these sort of humanized paths can be identified. What could potentially be identified is the sort of empirical metamathematics. That is of all possible mathematical theorems, of which there are an infinite number, the 3 or 4 million that humans have chosen to publish in papers about mathematics. How do we pick those particular ones? What's special about those particular ones? That's something that we could imagine having some statements about. Now, I think I've certainly looked for many years, probably 30 years or so, for kind of signatures of kind of the human aspect of why did we pick these axiom systems for mathematics and not other ones. And there's a little bit I figured out, but mostly I think it's sort of complex accidents of both history of mathematics to some extent and our experience of the physical world, which in turn depends on the particular sensory systems that we have. And it's kind of a very much, it's on us, so to speak. But exactly being able to draw the line from the way we are sort of as biological entities, so to speak, to how we got the particular mathematics we got with arithmetic and geometry and things like that, one can get a certain distance towards that. And I think there's a certain amount one could say about what kind of mathematics it would be conceivable that, mathematical observers like us could possibly explore. But I think, is there a more detailed characterization of math that humans pick out, of all the infinite number of possible theorems, the ones that we choose to study? I don't know yet.
I think there's like your point of we are part of the physical world, and the way we reason is based on the fundamentals that surround us. So we could look into the stars, we could look into study them, we could look into the physical space and then study them. And LLMs, and I read your paper as well on ChatGPT and the website, is very much of like just adds a one token based prediction and based on just the corpus of the training data set. So like, is it like in a way it is smart, but it's not intelligent to an extent that it scales to every reality of the world? And I thought that was really interesting, because what would it take it to be able to scale to reach to that point of AGI, especially that better understanding on computation, better understanding on reasoning, and then the ability to solve proofs, even as right now it's even unable to solve a very tough coding challenge as well. So with without knowing it in its purpose, how can it become more intelligent with the capability of computation involved?
I mean, computation is this thing that isn't intelligent like humans are intelligent. Computation is a very alien form of intelligence. I mean, humans have certain kinds of intelligence characteristics that LLMs, have comparable versions of. And when it comes to, imagine an LLM or imagine a system, a computational system, it's just doing all kinds of computation. I mean, I've spent a large part of my life studying sort of what happens in the computational universe. If you just essentially pick a tiny program, even at random, for example, what does it typically do? One might have assumed, as I did in the kind of beginning of the 1980s, that if the program is sufficiently simple, the behavior that it produces will be somehow correspondingly simple. Turns out that isn't true. It was a big surprise to me. I think, I gradually watch people sort of becoming more and more used to the idea that that's really the way things work. And it's kind of charming because there are always people who kind of just, you can see their intuition just hasn't grokked that particular point. And they keep on saying, but look, you have to, to get this kind of behavior, you have to make the program more complicated, or this thing we're seeing, it has to be something where there's some very complicated, what if you made more complicated rules? What if you did this and that? You don't need any of that stuff. I noticed that, I don't know whether it's partly a younger generation or something, but there are people to whom things like the phenomenon of computational irreducibility that I started talking about 40 years ago is obvious. I wrote this big book about 20 years ago now called New Kind of Science. And in the preface to that book, I kind of said, a lot of what I've said in this book will seem completely shocking and implausible to people now, but in time it will come to seem completely obvious. There's now sort of a subpopulation to whom these things are completely obvious, which is nice. That's the way progress gets made. I think that this point about sort of, well, what happens when you're doing lots of computation? Lots of complicated things happen. Those things are very non-human. They're the things that are out there in the computational universe. The things that we humans have sampled in the computational universe. We've sampled just very, very tiny parts of the computational universe and decided those are the things we care about. But there's an awful lot else out there. And if you say, well, take this sort of super AI that's computationally, enhanced, it can go off and explore all these parts of the computational universe that have not been humanized, so to speak. So what happens when it does that? Well, we've got this thing that's going off and computing lots of things that are not really things that resonate with the things we humans think about or the things we humans can kind of fit in our minds. But that's very much like what we already see happening in the natural world. The natural world is, in a sense, full of computational processes that are very non-human. I mean, sort of notably, people say, the weather has a mind of its own. It's those processes of fluid dynamics in the atmosphere. They're doing all kinds of computations, just like the neurons in our brains are doing all kinds of computations that happen to be based on electrochemistry rather than fluid dynamics. But it's really, at some computational level, it's very much the same kind of thing. And I think that's the limiting case, is when you amp up the computational capability, you go off into the computational universe and you get things that are essentially alien intelligences, not well aligned with human ones. And I think the chasing of AGI, while charming, is it's kind of interesting to me that the things people say about it and the risks it has and all this kind of thing, if you read what people wrote in the early 1960s, it is basically word for word what's being said today. The only difference is, it's really charming, if you take paragraphs that were written in the early 1960s about how, our species is merely a stepping stone to the ultimate, digital AI future type thing. The only thing that's different, the only thing that tells you the age, is that the kind of sensibilities about society and the kinds of things that people say about sort of the structure of society, they're a bit different back in the early 1960s than they are today. But that's the only way you can date it. It's just like, when you see a movie or something, you can date it by the computers that you see in the movie type thing. So in this case, you can date the things that are said by sort of the quirks of their time, so to speak. But the main sentiments are very much the same. And when you say, well, what does it take to make sort of the super AI? Well, it's, you'll keep on saying, well, that super AI isn't quite like a human, and because it has this feature that's wrong, it doesn't have mortality, it doesn't have children, it doesn't do this or that. And the only thing that will satisfy your criterion of being exactly like a human is pretty much a human. Now, as soon as you go away from that, you're getting to things which, for example, have attributes that are deeply non-human, like being able to do sophisticated computations, which we humans can't do. And I remember when Wolfram Alpha came out, people were using it to kind of fuel Turing test systems. And the total giveaway for those Turing test systems, you ask a bunch of random questions about all kinds of different things. If it could answer those questions, it wasn't a human, which is kind of the opposite way around than you might think, where you think the human is the pinnacle, and that's what you're looking for. So I think the thing to understand about sort of what happens when you kind of amp up the computational capability, where do you go? Well, you go to things which are in part a kind of like sort of the generic computational universe, which are a bit like the generic physical universe. Lots of processes that we humans just don't care about, where we say, yes, there's something sophisticated and computational going on in that waterfall or something like that. But the details of it are not things that we engage with in our minds. We don't really care about those details. Now, I have been curious recently, actually, about the following question. If you look at, cats and dogs versus us, the sizes of their brains are maybe 10 to 100 times smaller than ours. And somehow, just as we saw in the development of LLMs, there's sort of a threshold at which things start to happen. Like you start to be able to get compositional language, which presumably the cats and dogs don't have. And we do have, and we're able to take our thoughts as they are in our brains and sort of package them up and turn them into language and transmit them to another brain, which can then unpack them and get something which is a reasonable approximation to the original thought in the first brain, so to speak. At what point do we get to compositional language? It's something our species invented. Maybe some other species maybe have partial versions of it, but we're the only species we know that's really gone the distance with compositional language. And there is a question, if we had 100 times the number of neurons in our brains, is there another level of kind of sophistication or abstraction that we can get to? What would it be like? I think the downer with that whole story is it will be like something that we humans won't understand or appreciate. It's, and like the natural world, which is full of computation that we humans don't understand. I mean, in a sense, science, natural science, is this attempt to find a bridge from what actually happens in the natural world to what fits in our kind of finite minds. And there's certain kinds of things we've successfully bridged. We've successfully gotten kind of human level narratives about some of the things that happen in the natural world, but others we have not. This whole idea of computational irreducibility tells us that there are lots of things in the natural world where we just won't ever get that sort of short narrative description of what's going on. I think that that's kind of a thing where, yes, you can have all sorts of sophisticated things happening that are far beyond us humans, in the same way that nature is beyond us humans, but it isn't quite as exciting as you might think it would be, so to speak. It's just something, it's like we're already probably in the position where there's a civilization of AIs out in our world that are kind of autonomously doing lots of stuff, whether they're selling us ads or whether they're bidding on ads or whether they're doing something more sophisticated and more interesting than that. I don't know. But there's already sort of the civilization of AIs that's out there running, many aspects of which we don't understand. We look inside, we can say, well, there's this distribution of activations in this neural net. What does it mean? Do we understand it? No, we don't. Does it matter that we don't understand it? Not really. I mean, it's the same thing. We've lived through a period of history, about 100 and something years, where we sort of did understand how the machines we built work, or the devices we use work. I mean, back, before the Industrial Revolution, if you wanted to get from here to there, a horse was a pretty good bet. And you could operate a horse without knowing how a horse works inside, and that's how people did it. Later on, for some brief period, you get to, well, yes, you can understand how the steam engine or the car works, and that's a period in history where we could sort of understand those things. But I think that period in history is kind of coming to an end, and I'm not sure that there's anything so dramatic about that phenomenon.
Mhm. And that's very interesting because we do not fully understand the computations that happen around us in reality, and we also do not understand the computation that happen that we surround ourselves with, that we create some parts of it. But like to an extent, in like if let's say autonomous AI agents are loose and then they speak in a different language and between themselves, because they don't technically need to speak and communicate in English or a human native language as well. Like they could transfer knowledge between different systems with a different type of mechanism that they could invent over time. How likely is it, do you think, that that sort of an intelligence of like creation is possible with these type of systems, given that they have access to more of each other's knowledge?
Well, there's a question of how do humans transfer knowledge from one brain to another? Each brain has a certain pattern of, weights and activations and who knows what else that encodes knowledge in that brain. Somehow that, brains aren't identical. You can't just pick up, the pattern of activations from one brain and stick it in another. You can't even do that with computers. Computers, if you took a computer that's been running, it's been running its operating system for a while, and you say, let me do a direct memory, memory transplant from one computer to another, it's not going to work. And nor is it with brains that have had different experiences, et cetera, et cetera, et cetera. So then the question is, what's the transfer protocol between brains? And the answer is the only transfer protocol we really know right now is language. And what's happening in language? You're taking all those details, our 100 billion neurons are firing in all kinds of ways, and somehow you're organizing those into this stream of a fixed set of tokens, 50,000 words in typical language. You're taking all of those 100 billion neurons and all their detailed firings, and you're sort of putting them through this thin path of this limited set of words and so on. But that's important. You have to do that because there's no way to do a sort of direct transfer from your 100 billion neurons to my 100 billion neurons. It has to be done through some kind of encoding that can be encoded at one side, decoded at the other side. Now, could you imagine a 1,000,000-word language being used by the AIs? Yes, you could. And in fact, that's a thing when it, what would it look like to have a 1,000,000-word language? Well, things are a bit shallower. You don't have to, in English, I might have to say, the big red dog or something, but in a 1,000,000-word language, there might be a single word for that. So what you end up with is sort of less thinking, less processing, more kind of just sort of the syntax is richer. So you can kind of describe more. But it's still the case that insofar as the world is an infinitely varied kind of computationally irreducible place, you will run out of sort of descriptors fairly quickly. Even if you have 1,000,000 words, there'll still be plenty of things that are, that particular shape of tree. You're not going to have a word for every possible shape of tree, every possible shape of cloud, something like this. You might have words for, and we typically have words for, 10 different kinds of clouds. And maybe, you'd have words for 10,000 different kinds of clouds, but there's an infinite number of possibilities. So it doesn't get you that far to do that. Now, I mean, there are other things you can do to transfer kind of from one mind to another. I mean, another one that's kind of a fun one to think about is we form mental images, but we don't have a way to transfer those mental images other than by kind of describing them in words, or maybe if we're really good at drawing, we can, draw it and show somebody the picture. That's a very slow process. It's about as slow as if you had a dog who wants to communicate in English and they're, typing with their paws on some big, pad or something. So, but you could imagine, for an AI, it has the ability to, it can generate an image, and we can imagine a situation, maybe even from brains, where, we're picking up neural signals from our brains and producing, a little display of this is my mental image, so to speak. And that's probably a much higher bandwidth communication channel with another brain than our one-dimensional languages. I'm not sure exactly how that would work, because it's kind of a thing where there's a way that people say a picture is worth 1,000 words or something, and maybe this is a way in which you can get sort of a higher bandwidth communication, but still you have to sort of actualize things in some. You have to have some way in which you have taken all of the detail of the world, which could be encoded in different ways in different minds, and somehow standardize that so that you can get, so you can get something that can be sort of transported to another mind whose structure is different. So yes, I mean, it's perfectly possible that the AIs can invent their million-word language, and maybe they can invent something that goes beyond kind of. There are creatures that, the cuttlefish, for example. Cuttlefish have chromatophores in their skins, and they have patterns. Then cuttlefish presumably communicate through something a little bit like mental images. We don't understand what they're saying to each other, but you can see a cuttlefish has all these waves of color and so on, and other cuttlefish respond to those waves of color, and that's a sort of different form of communication. I don't know whether that's I'll be a little embarrassed if cuttlefish are being more sophisticated in their communication than we humans are being in all the kinds of things we've developed with language, but I don't think it's easy to tell.
That is very true. And it's like I think the communication also develop in the reality that we are exposed to, and then that like the physical reality that's around us. If the fish adopts to communicate in that way, and then we adopt to communicate because of our sound and ability to make sound. And the same goes, I assume, maybe the AI's access to certain data, and then the way it can compute certain things in the realm of and in the boundaries of computers, and potentially even the quantum as well, quantum computing.
That's a different issue. I mean, look, the one thing about our description of our world is very much based on our senses, and you know there are many aspects of our senses that are pretty specific to us. Like, for example, our brains think in kind of millisecond or even 100 millisecond time frames. But the speed of light is very fast for the distances we're dealing with in our typical environment. The speed of light is very fast relative to that. So in a typical situation, we are kind of seeing the structure of space around us in one gulp before we can think about it. If you're a piece of digital electronics running a million times faster, then that image of the scene doesn't necessarily have to come in all in one gulp. You can be seeing those individual photons arriving, and it's really just a matter of the human kind of presentation of the scene that we choose to make it into a single image, rather than just this is a bunch of photons arriving. And I think that's it's the question of the sort of the sensory data that we get. If you're an AI that's being fed by a bunch of IoT devices, you've got a million IoT devices from different parts of the world that are kind of feeding you information. I don't know what you conclude about what you discuss about what happens in the world. It's not quite the same. It's the sensory system is very different. If the kind of we have some number of tens of millions of kind of touch sensors on our skin and so on, but imagine that you are an AI that has, I don't know, 100 million IoT sensors all in different places. There may very well be things that would be your kind of words for things that happen in the world, where you have a word that means kind of, I don't know, some kind of strange correlation between the observations of different IoT sensors in different places, something that we don't have any experience of, and don't have any way to, have not chosen to have any way to talk about. But in terms of the quantum side of things, it's sort of interesting, because sort of the essence of quantum phenomena is that instead of having this sort of one path of history where definite things happen, like in classical physics, in quantum mechanics, sort of the big idea is that there are many paths of history, and we typically only get to see sort of some kind of probability of different paths being followed. But more specifically, what happens is inside a quantum process, or a quantum computer for that matter, there are sort of these many threads of history that are being followed. The thing is, and the thing that makes, I think, quantum computers not a very practical possibility, is that we humans want a definite answer. It isn't adequate to us. Our brains are actually quite architected so that we try and aggregate all the different things that are going on in our brains to get definite answers. We want, probably maybe every 10 times a second or something, our brains, aggregate all these nerve fibers, go to these basal ganglia and so on, and they seem to be aggregating the thoughts that are coming from all those different nerve cells. We're reaching some kind of consensus about what to do, maybe 10 times a second. And that's kind of how brains are architected and how our experience of the world works, that we think definite things happen. One thing happens, another, then another, then another. In quantum mechanics, many things are happening in parallel. One could imagine a quantum brain where it could have many thoughts in parallel. That brain isn't our brain. Our brain doesn't work that way. And, could we imagine kind of an AI that operates where it's sort of thinking about many things in parallel? Sure, that's sort of the story of distributed computing. Interestingly, distributed computing is something that's very hard for people to wrap their brains around. I mean, distributed computing, when it's just like, well, I'm just going to distribute, the different, I'm going to use parallel table in Wolfram language or something and just do a table of values where each element of the table is being computed on a different core. Well, that's reasonably easy to understand. But when things get more complicated, we humans are remarkably bad at understanding kind of sort of parallel distributed computation going on. And I think that's very closely related to the fact that we have this fundamental kind of design of our brains that tends to sort of sequentialize everything. And that's really the way that we think about the world, is in this sequence of events through time, so to speak. That's something, yes, the AIs can avoid that, but the things that they're doing when they avoid that are things that are very non-human. They're things that are not, are as unrecognizable probably as the processes in nature.
And then there's the approach of like making AI more like us, because in a way we are kind of creating it, and then there's also approach where it can go do its own things. And I want to maybe tie it to education as well, and because of like from taking the computational thinking to like traditional hand calculation in schools that we have. Like, what are some of your thoughts about that? And I saw that there's the separation of like College of Computer Science and College of, I think, Computing, that's happening. I'd love to learn more about what that really means for future, and that for students to.
I don't have a clue. I would think that was some piece of university politics that caused that to
Really?
happen. So that's
Okay.
probably not a significant
Okay.
intellectual thing. But there is something which I think is more intellectually significant, which is that computer science has a funny history. I mean, it's and it has become kind of the trade. For the most part, people study computer science as for the trade of programming, to learn the trade of programming, so to speak. I think that's a trade which in many ways is going to be a trade that goes the way that many hand trades have gone, which is it kind of goes extinct, except for a small number of practitioners. I mean, back when I started doing computing, assembly language was the language anybody serious used. And I remember people telling me back in the 70s, there's this newfangled language called C at the time, and people telling me, it's never going to catch on. Assembly language is the only thing you can really program a serious application program in. Well, that, you're smiling because that's ancient history, and it obviously didn't play out that way. We're in a situation today where a lot of programming gets done kind of in a very step-by-step way with kind of standard low-level programming languages. My large part of my life work has been automating that process, figuring out what are the lumps of computational work that are repeatedly needed, just like figuring out the words that one would need in a human language to express things, figuring out the lumps of computation that one needs to sort of express the kinds of things one wants to express in thinking about the world computationally, and just implement those things and do it in a sort of coherent way. That's kind of the story of Wolfram language, is the story of trying to make sort of as high a level as possible a language for expressing things computationally, so that once you can think about things computationally, then you have a medium for expressing those things. It's kind of the analog of what happened with mathematical notation back 500 years ago, where mathematics went from being expressed with natural language words to being expressed in a kind of streamlined notation. That's what launched algebra and calculus and basically all the modern mathematical sciences. So what we're trying to do with Wolfram language is provide kind of the notation that allows you to talk about the world computationally and kind of launch computational X for all X, so to speak. And I think, learning how to sort of think computationally about things and learning how to formulate things sort of so that you can express it to our computational language, that's a very valuable thing to do. That's an important thing to do. Learning how to write low-level Java code or something to do something, or Python code or whatever else, is one of those activities that I think is, its days are numbered, so to speak. I mean, I see that from what we've done. I see, CEOs and CTOs of lots of tech companies who use our technology all the time. The people in the trenches just writing code aren't using our technology. It's a very bizarre kind of inverted situation, which I finally understand, because the typical programmer doesn't expect that they have to do serious computational thinking. The typical programmer is I'm doing this, I'm writing this piece of code, I'm writing another piece of code. It's, I'm writing it according to the spec. The formation of the spec is a piece of computational thinking, but that's not what the programmer does. The programmer is the kind of the artisan or something who's actually, grinding the lenses or whatever, not the person figuring out how the optical system is supposed to work. And so what you see is this sort of weird phenomenon where people can, use our computational language to do all sorts of things in a few hours, and then sort of the programmers come in and they take months to do the same thing, which is kind of just a precursor of the future, which is that low-level programming function just doesn't need to be there. It can be automated away. It helps now that we have LLMs that you can use, like our notebook assistant system, to really go from sort of a vague natural language description to something which is like, here's a possible meaning to what you said in computational language. You can look at that and you can say, yeah, that's what I meant. Or you can say, you missed the point, try again, or you can adjust it yourself. But that seems to be a very productive way to work, that you go from even a fairly vague understanding of what you're trying to do to something where the notebook assistant, the LLM, is producing kind of this sort of precise version of it in our computational language that is a language that is set up specifically to be sort of readable by humans as well as writable by humans. And so I think that's, in terms of the sort of the direction of education, learning sort of computational thinking, very important idea. Learning the craft of programming, in standard programming languages, I think, that's about, it's going to go the same way that assembly language programming went, back, believe me, at the beginning of the 80s, when I was the first big computer system I built, which started my first company and so on, was, it was big system written in C. And people were saying, you can't be serious. It has to be an assembly language. You can't, that's not a realistic way to set things up. Now, to be fair, Unix had already been written in C by that time. So that was sort of a silly thing to say, but people say silly things all the time. That doesn't, but I think, what we're seeing right now is, from an educational point of view, learning how to think computationally about things, which is a lot about kind of getting a sense of how one thinks about lots of different kinds of things in the world computationally, whether that's thinking about how one thinks about images or sounds or geography or whatever else computationally. That's the really valuable thing to do, I think, at an educational level, not kind of the craft details of, writing, I don't know, object-oriented programming, methods for this, that, and the other thing. I mean, I think that's kind of that will go the way of assembly language, so to speak. But I think, and I think that the idea, it's kind of nice. I didn't plan it this way, but we've kind of arrived at this sort of unique place in the technology universe with the technology stack that we built, because we have this language that is really expressing the world computationally. It's not talking about, how to set variables. You can set variables if you want to, but that's not the thing people most do. It's kind of expressing at a high level, expressing things about the world and things that you're thinking about in a computational way. And that's kind of, so for me, and it's nice to see how that dovetails so successfully with kind of the world of LLMs, where the LLMs provide this sort of linguistic interface to this underlying kind of computational representation of the world.
It's in a way that they complement one another really well. Brings the capability to do. And for someone like who is a student maybe right now and I don't know, freshman in college or in high school or before, how can they think more differently when it comes to adopting the skills to think computational and then not be stuck in just being a focused on that systemic repetitive coding or programming language itself? Like
Yeah.
how can they change the way they think to
Right. I
be
mean,
relevant?
I've tried to build a bunch of tech to make that possible. I think it's unfortunately fairly unique in the world. So it's kind of like, the message has to be learn our tech, because that's the best path to get to sort of computational thinking. Now, in terms of what to learn, what to study in college, for example, I think that there has been a tradition for decades that sort of that the best thing to do is to be extremely specialized, to learn, a very particular kind of set of almost mechanical skills, and learn this very tall tower of mechanical skills. That has been a way to be sort of valuable in the world for quite a while. I think it's going away. I think that those things which are those sort of tall towers of specific sort of personal functionality are the things which are readily automatable, and increasingly will be automated. There were sort of blocks to automating those things that came because we didn't have LLMs. We didn't have kind of a linguistic interface. We didn't have this way of operating that sort of had this layer of this sort of humanizing layer. And I think that the sort of my advice these days to people who are like going to college and so on is learn about a bunch of different things. Try and learn as broadly as possible about different ways of thinking, the ways of thinking that might exist in, pure mathematics versus biology versus philosophy versus history. All these different fields have different ways of thinking. It's very useful to learn all those kinds of things, as well as to learn the facts of a lot of these different fields, because I think the future is much more generalized. It's much more about generalism than specialization. I think computational thinking is a tool for general thinking. It's a tool for general thinking in the same kind of a way that philosophy, for example, is a tool for general thinking, or logic is a tool for general thinking. I think it's a very broad tool and has the additional kicker that computers can help you do it. So if you're doing philosophical thinking, so to speak, you're kind of on your own for the most part until very modern times. With computational thinking, once you've formulated your thoughts in that kind of precise computational way, then you're off and running, able to get a computer to help you, sort of to give you a kind of superpower to go beyond what you can merely do with your mind.
And when it comes to especially like when you started your company and then looking at from the lens of entrepreneurship and then building conviction into well everyone says no but saying no, this I'm sure this is what are some things that you experienced over time that help you build that conviction? And for other entrepreneurs out there as well, I think that would be a very valuable for them to hear too.
Well, it helps to have been successful in the things you've done, because after you've been successful, you see a pattern of, yeah, it worked, even though people said it couldn't possibly work. And, the things I've tried to do have gotten bigger over time. I was lucky enough to be pretty successful as a teenage particle physicist, which is kind of a weird thing to do, but that was, and it happens to be and then, I was built my first big computer system right at the beginning of my 20s, and that turned into my first company, which I made many mistakes. I was a pretty successful academic, so those were all kind of, yeah, I can do those things, and these things work out fairly well, and that gives one the confidence to sort of say, yeah, well, this thing I'm thinking about doing, I don't really care what other people say because I'm pretty sure I know what I'm talking about. Now, at some level, my own way of thinking tends to be very kind of foundationally based. That is, I try to really get to the root cause of things, the kind of the foundations of how to think about things. And one feature of that is you're kind of, if you can do that, you're sort of always on bedrock. It's not the case that somebody's going to come along and say, wait a minute, you misunderstood that. It doesn't work that way, because you built your thinking on this very, very solid foundation. And I don't think at the very beginning, I don't think I was doing that. I think I was more, and then it was more important that I had sort of practical success in doing the things that I was doing and built sort of confidence from that. But I think now, I'm doing things which are sufficiently far outside kind of the things that there's really a kind of an ambient understanding of, that the only way I can have any belief that what I'm doing makes sense is if it's sort of built on bedrock. And for me also, I do put a fair amount of effort into explaining what I'm doing and, providing exposition of various kinds. That's very useful to me, because that's part of the way that I can tell that I know what I'm talking about is, can I explain it to people? If I can't, well, that's not a good sign. And, it's like, get the foundational understanding, be able to explain it to people, get to the point where you're confident in what you're saying, so to speak. And, people will say all kinds of crazy things. And it depends on whether the things you're doing are kind of how far out from what's been done before they are. The further out they are, the less likely you are to find people who will really kind of appreciate them, because to get to the point of thinking like you're thinking is often quite a bit of effort. And if you just say to somebody, hey, what do you think of this? There isn't, they just don't have that background. Now, it's also the case, and I think it's worth listening to what people say, because even when they say something that on the face of it is like, yeah, they kind of missed the point, sometimes that thing, in my experience at least, gets you to think about something in a slightly different way. How can I explain? That's a confusion I've never heard before, so to speak. How can I possibly explain something based on that confusion? And as you try to do it, you realize, wait a minute, this is actually interesting. I now understand something better than I understood it before. But I think that's, it has to be said that for somebody like me, I've done a bunch of things which I suppose from the outside look like they're high risk propositions. From the inside, nothing I've ever done has ever looked like it had any significant risk. So in other words, one has for me, it's like, I'm going to do this project and I kind of see my way through this project and I think it's going to work. And that's, I don't really now, I kind of have this kind of, I'm convinced it's going to work. I'm not worried about whether it's not going to work. Now, that doesn't mean that I don't look and say, well, here's the 10 things that could go wrong. Let me try and figure out how to avoid those 10 things that could go wrong. But I have no doubt that the project is going to work. Yes, there could be some bumps along the way, and there could be things that, come in and try and block it. Okay, I'm going to get rid of those things. I'm going to figure out how to push past those things. But I think that's kind of my approach. Now, it helps when you're doing entrepreneurial kinds of things. I've mostly built products that I want myself. I mean, I'm user number one for most of the things I built. So this is for Wolfram language, for example, that's the thing, that's my kind of computational superpower, so to speak, is that I can use this thing that I've just been building for the last 40 years, and it makes me really efficient. And it makes me, relative to people where, it's kind of a funny situation, because back in the 70s when I was a kid, I started using computers. Pretty much theoretical scientists didn't really use computers. And so that was a weird kind of secret weapon that I had. And I it's only years later that I kind of realized how surprised I should have been that other people were not using these tools. And then I started building tools. And, I think we're in this situation where, well, the tools I built are available to everybody. I mean, I get to run a version that's a few months ahead of other people, but that's about it. It's, other than that, it's kind of available to everybody. It's not clear people would want to run the version that's the pre-release builds of the system. I was just running one this afternoon and it froze horribly on me. So I don't think it's not, one shouldn't wish for that, but it's still, it's really, but the most important thing for me is it's sort of this superpower tower of capabilities that I've kind of, you know, gotten built for myself that really allows me to get a long way. And by using those tools, it's kind of like use the tools. Now, having said that, in terms of like building companies and things like this, you have to be sort of, you have to be capable, I think, of thinking about a broad range of things, which comes back to this whole education question of, do you become a specialist in some very particular thing, or do you just learn to think in general? And, I think the thing that, you run companies and things and you kind of, lots of different stuff comes up. And the question is, can you apply whatever intellectual or analytical skills you have to all those different things that come up? Or do you say, well, I know about this, but, about that, I'm just going to delegate that because I don't really understand it. That's usually, I know in the history of my company, I started my current company, 39 years ago now. And it's, there are areas of the company which I just was never that interested in. And, things about sort of the operations side of the company and so on, and some of the commercial sides of the company. And, I discover in the end that anything I don't understand isn't done very well. And that's not because the people are, it's just, you can't really manage it well unless you really understand what's going on. At least that's my experience, and I think it's, I really feel for people who try and run, technology intensive companies and don't understand technical kinds of things, because it's like, people tell me all the time, oh, that's impossible, et cetera, et cetera, et cetera. And it's like, well, why? And it's like, oh, because, this or that technical thing, blah, blah, blah. And I'm like, well, did you think about this? And they're like, oh, that's an interesting idea. Or, sometimes it's like, we just, this just doesn't work. And eventually it's like, for me, it's like, well, show me the code. And usually, I have to say, in scale of company that we have, usually the show me the code thing, I never actually end up seeing the code, because before I see the code, I'm asking all these kinds of questions about how it actually works. And there's usually this moment where it's, well, we didn't think of that. And you never actually have to open up the code. But sometimes it's useful as a backdrop to have the code on the screen. And then because that's kind of makes a reality to the, what does this actually do? Often it's complicated enough you can't possibly see what it does just by looking at it on the screen, but it still it sort of grounds the discussion about what the general picture of what's going on is.
And it's like the way to think, and then do your questions are actually unfolding what's in their mind, and then they realize where the
Right.
problem is at, and they didn't ask they didn't ask the right questions to the problem to go down and deep. And then to your point about like conviction, it is very powerful to have that strong bedrock, that because then that makes you less fearful. I think a lot of the entrepreneurs, they fear of failure, and then that fear of failure leads to the failure. Whereas you already know, I know my foundations are right at first principles. Then that really builds the conviction.
I mean,
Before,
let's be realistic. I mean, somebody like me is something of an optimist, right? I always believe that this project can be done, and such and such a project can be done, even though the objective information does not necessarily support that. I mean, it is just because I think I can see how to do it, and I think I'm confident enough that if there's some bump, that I can overcome that, so to speak. And I think that's that is a more, it's partly personal psychology, partly it's experience from doing things. But I would say that, you know I suppose at some level it's kind of, I don't know, what does it matter, from some point of view, right? I do projects, I'm pretty sure they're going to succeed, but at some level it's like, well, if it isn't succeeding, I'm going to figure out. I mean, I guess I've never really had a project that's just gone splat in my whole life. I mean, I've never really, I guess there's one that I did once, a long time ago, that was a kind of stupid project I should never have started, that I kind of delegated a large part to other people. And, eventually I just said, this is not working, and pulled the plug. But usually, major projects I've done, they've always ended up, getting to the finish line. So now, what the finish line looked like relative to what I thought the finish line would be like is not always the same thing. In other words, they got to a finish line, but not necessarily precisely the one that I thought they'd get to. Often, the one they get to is much better than the one I thought they'd get to. Sometimes it's like I'm really putting a lot of effort into one aspect of the thing, the product we're building or whatever else. And it turns out as we build it, we realize there's this other thing. And then we realize people are really going to care about that other thing. And the first thing that we were initially building it for, it's just nobody actually cares about that. That wasn't the important thing, but we couldn't see the thing that people really do care about without having built up kind of a level of capability. I mean, I'm thinking even this afternoon, I was doing a design review, which we live streamed, as we do most of our design reviews, about a fairly abstruse area of systems engineering, which has caused us to realize that there's some more general things that are worth building that are much more important, I think, than the sort of systems engineering details that this started from. So it's kind of an example of how that works. But I think it's I don't know, I think sort of the trick is to have a belief that there's a path to succeed, and to be able to divert in real time. I mean, sometimes you'll see with companies, it's like, we have a plan. Well, it turns out the plan isn't a very good plan. And, you discover that halfway through. And if it's just like, we have a plan, we're going to follow our plan, that's not a good thing. I mean, in my company over the years, I think we've developed a fairly good culture of being able to sort of pivot plans. I mean, I'm doing this right now with a couple of projects, actually. It's always, hey, you can't pivot that. We were on this path. But it's like, so you have to put a certain amount of, pressure and thought into the whole thing to make that work.
It's like in a way the scenario planning as well. And I know we're almost at time, but I would like to thank you very much for your time. This has been wonderful to hear your thoughts and about AI, about entrepreneurship, about your journey, and about the world around us. It's been a pleasure. Thank you very much.
Thank you.